So last time we left off with the density operator equation of motion, and I derived it. It was very easy just using the Schrodinger equation. We saw that it's the commutation between h and rho. And I just wanted to give you a quick example of this. Of course, the usual example is a single spin 1/2 particle. We can imagine a Hamiltonian that's given by this. So this is that gyromagnetic ratio thing, and this is a magnitude of some B field. So it's basically a spin 1/2 guy in a magnetic field pointing along the z direction. So if you have this Hamiltonian, then you can calculate, of course, the equation of motion for the spin 1/2 particle. And what you would get is, of course, remember that for spin 1/2, the rho is given by the identity plus B dotted into sigma, where B is this vector of 3 numbers, and this is a vector of the Pauli matrices. So if I differentiate this with respect to t, I get an equation for all the b's, really, because the time derivative doesn't do anything to the identity. So we get an over 2 here, and this becomes right, dbx dt sigma x plus dby dt sigma y plus the dt sigma z. That's on the one side, and then you have a commutation relation between h and rho, and that would be the commutation relation, right, between these guys and rho, but that, of course, is just it doesn't commute with the identity. I mean, it commutes with the identity, so that part's 0. So the only part that you have to worry about with the commutation is the b dot sigma part. So, so that's okay. So then all of this, right, you can use the properties of the commutation relations of the Pauli matrices. Just use one of those identities for the commutation between sigma, z and sigma x, y, and z. So the commutation between sigma z and the sigma z part, of course, will be 0 because the thing commutes with itself. So you're left with just the commutations between x and y. And so using those identities, what you would find is that this is equal to minus a quarter. You got this gamma bz. This is the z component of that b field. And what you would get is bx sigma y, that's from the commutator between sigma z and sigma x, and minus by sigma x, like that. And so what you would find then, oh, and there should be an I. Yeah. So what you would find then is that you can compare the coefficients of sigma y over here and sigma y over here, and then you can compare the coefficient of sigma x over here, sigma x over here. So and then of course there's no sigma z, and all those are independent. Or you can write this out in terms of 2 by 2 matrices and set all the entries equal to each other. But the point is that you can show, and I don't want to spend too much time on this, I also might be off by some factors here, but the basic idea is here, and I think I'm also missing a 2. Yeah. I think it's 2i, and then it's these sigma I, sigma z things. So if you compare the coefficients, so this is a half here and a half here, what you'll end up getting is that dbx dt, that's this part, has to be equal to whatever's multiplying sigma x over here. And that's going to be minus, or let's see, is it minus? No, I guess this is plus. Yeah, I'm gonna get these signs backwards, but it's okay. So this, and it's, you divide by h bar, so it's bz gamma over h bar. Let's see what we have here, sigma x, and it's by, right? It's this guy. The other one, the by should be with the opposite sign. Yeah, and then dbz dt, there is no, this is the bz part, there is no sigma z, so it's like plus 0 sigma z, so that's equal to 0. So anyway, if I did this correctly, which you can do, it's good practice if you want, but I'm not getting these signs right, I don't think. But the point is, what you can show is that the time derivative is, you see the x component is equal to the y one, and this y component is equal to the x. So if you write it in vector notation, that just becomes b cross b, like this. So the if b is pointing along the z-axis, right, then the z component, of course, if you cross anything in the same direction, then that's 0, so that gives you this equation. And the x and y components, the cross product gives you the right flip between, x and y and x. So you should get this, and this is just the equation for the precession of a spin, a classical spin in a B field. So this is the classical equation for a spin moving around in a B field. So you see this B vector of the row matrix behaves just like you would expect for the classical spin. And that makes sense because we saw that, the expectation value of the spin is really just given by the B vector, or I guess it's proportional to because of the H bars. So that's a really quick one. I'll probably update the notes with a more careful derivation of this to get all the signs right. I can never remember where the H bars go for this problem. It depends on how you define this. So I'm sure I got their units wrong, but that's the basic idea, is that you can use this equation, right, for any particular Hamiltonian that you want. And then if your row just depends on the sigmas, then you can use all those properties of sigma matrices to, derive like the equation of motion for the B vector inside rows. So that's for spin 1/2. Any questions about that? It's a little hand wavy. I'll fix it in the notes today, but yeah, sorry, I can never remember where the I's and H bars
Could
go.
you I see what you said there, but what was could you just remind me the difference between the capital B cross the little b? Was it just right there? You said gamma, the cross product there.
How I went from here to here?
Yeah. What was that again? I mean, I could rewatch the video, I guess, but
no. So okay, so I get. Do you get how I got these three equations?
Yeah, those are easy.
Yeah. So it turns out that I can write this as a vector equation because I have three components, x, y, z. So I can write this as a time derivative of a vector, right? I can just write this as dt of bx, by, bz, and that's equal to minus gamma some other vector, and this other vector must be bz by, bz minus bz, bx, and then 0, right?
Yeah.
Well, but this is just b cross little b. If
I
b
see.
is just pointed along the z direction.
I see. Okay. All right. Thank you. That makes sense now.
Okay, great. And I'll fix it up in the notes, but it's not so important. I just wanted to give you a brief example of the spin 1/2. I think a more interesting example we're going to do in a moment, but before we move off from this discussion of the density matrix, I wanted to tell you the postulates for of QM again, but this time using rho. So postulate 1 using rho would become a state of a system corresponds to some rho, right, acting on Hilbert space. So instead of a ket, you now represent a state by a state operator rho, and it's it has trace equal to 1. That's the equivalent of the normalization. So remember before we had in the old postulates, we had that postulate 1 state is represented by a ket, and then you had normalization of the ket. Well, now it's generalized to include classical uncertainty and also to include, well, I mean, it's just a much better way of thinking about things because now you don't have to worry about the phase of the operator or of the ket or anything like that. So this is much cleaner. Then postulate 2, the probability. So this one's kind of funny. You want the probability, so now you have to. The second postulate, if you recall, had to do with the probability of finding a system in a certain ket. So, we have to do that again. So the probability of finding a system in state, and maybe we'll call it, we'll call it this because that's in terms of a projection operator or in terms of a state operator, so projector like this. So the probability of finding a system in this state, of course, which this is rho, is little p psi, and that's equal to trace, we know, of rho psi, right? So, so it's just like that. Remember, that's the kind of equivalent of psi. I'll put it in red, right? In the old postulate 2, we had psi phi squared as a probability. If we're in state phi. Here we're in state, we're described by this rho instead of phi, for instance. Postulate 3, that has to do with after a measurement. So after measuring an for some a, some eigenvalue of some permission a, which has an associated eigenvalue and eigenvector n, or if you want this is the eigenvector associated with that measurement. Then your density matrix transforms to just the projection, right? So it looks like this. So what's this do? This is the normalization, right? Here we see that in the end we get something that's proportional to this guy. And I guess this is a properly normalized eigenvector. It's just equal to that. But you see, it's the same idea. It's instead of kets now we just deal with these state operators. So if, you know, in the end, you're supposed to be in this eigenvector of the measurements, then, and you know, this is a normalization to ensure that the trace of this thing that you get in the end is 1. So it's exactly the analog of what we had before, except, you know, in terms of these rows instead of the kets. And then the Schrodinger equation, you know, for a closed system, you know, under the conditions that the Schrodinger equation holds, then the Schrodinger equation, which I derived last time, is just that. And then that's it. Those are the postulates rewritten in terms of rho. They're just cleaner this way because they let you incorporate classical uncertainty in your state description. And postulate 5, you could still have for multiple systems. For multiple systems, rho acts on the tensor product Hilbert space, right, of all the subsystems. And that's it. So instead, you can throw away the notion of kets, and each time you see a ket, you could instead describe it using this kind of projection. But you can do more than that. Instead of just having a single ket, you can have uncertainties, right? And which ket you have. So you can have a sum over different kets where you have different probabilities of being in those kets. Yeah, that's the idea. And you can redo all of the stuff we did before, just using that. So now everything is written in terms of operators on a Hilbert space instead of the vectors, which is kind of nice. Sometimes it's a little bit cleaner way of thinking about things. But yeah, any questions about that? And these new postulates?
So in this case, we are considering the phase as well, right? When we consider the
yeah, well, the nice thing about having this object is if I multiply the psi by a phase, then this guy comes in with the minus that phase, so the phases cancel. So rho, there's no ambiguity associated with phase, right? Remember,
okay.
In the old postulates, we had to say that it's all a physical state is represented by psi up to a phase, so we can multiply by a phase, and that's still the same state. So it's kind of annoying. And using rho fixes that because rho is always of this form, so there's no ambiguity in the phase.
Okay, thank you.
All right, so that's kind of it for the postulates. So let's now talk about some quantum paradoxes. And also computing, I guess. These kind of modern things. And so I thought it'd be important to cover them, although they're not typically part of a traditional course. I don't think I really learned about these until sort of later. So so a famous paradox in quantum mechanics, so-called EPR paradox, and one of the ways to talk about it is to consider the spin singlet state, which we've sort of been looking at for quite some time now. I demonstrated that it's a spherically symmetric state, right? And it's entangled. And you can imagine the following. So again, this is a tensor product, right? So this state, whatever it is, it's an element of a tensor product of two Hilbert spaces corresponding to two different spins. So you can imagine taking this first spin, right, and sending it off someplace, and then taking this other spin and sending it off to some other place, and then doing various experiments on it. And what you would find is that if you measure, and we know this is spherically symmetric, so no matter how you measure the spin along whatever direction you choose, you always get a 50-50 chance of being, you know, plus or minus h bar over 2 for the angular momentum. So there's always a 50-50 chance of that. But the weird thing is about this is that you see the first and second spins are always completely anti-correlated, so that if the other person over here, maybe, yeah, I should have made this red or something. If the other person over here measures the spin along that same direction, right, then whatever they get over here, say they got plus h bar over 2, the person over here must get completely the opposite result, because they're always anti-correlated. And that, it doesn't even matter what direction, it's whatever direction is chosen here. If the other person picks the exact same direction, they'll get perfectly anti-correlated results. And that's really weird if you think about it, because it means, you know, the paradox is it's as if, you know, the spins know about each other, that they know that the person measured in, like, say, direction X, that this one knows to be perfectly anti-correlated along the X direction, right? It's weird because say they weren't along the same direction, say this person measured along the Z direction, and this person measured along the X direction. Well, in this case, if this person measures along Z, then there would be no correlation with the X measurement, right? So this would be, so if this person measured plus h bar over 2, and then the person over here would measure, you know, completely uncorrelated values of plus or minus h bar over 2, and be random. So it's really weird. It's as if, you know, the two spins know about which direction they're going to be measured, but they don't. It's just that the concept of the direction of the spin is not an element of the reality. It's not recorded in nature. So it's free to have whatever correlations it needs to have in order to make the quantum mechanics work. And you can see that element of reality aspect of it by studying so-called Bell's inequalities. That's what I'll talk about now. It's a way of formalizing this idea that this direction of the spin, it doesn't have a real aspect to it. It's not an element of reality. It's just not a feature of nature. It's there's no such thing as the orientation of the spin.
So wait, so you're saying it's not a nature thing, it's not having a defined spin, so it doesn't have anything to do with that it originated from a central point, and that's why it changes. But you're saying that that's some construct of man, the spin, instead of nature.
No, I'm just saying that this idea that there's a way you can think about quantum quantum randomness, I guess you could say, is imagine the way you can think about it is imagine like a pie wheel where these would be the results of your measurements along particular directions.
Yeah.
And maybe it's, you know, plus h bar, minus h bar. And if you measure the spin along some particular direction, like B1, then you'll get a plus h bar over 2. And maybe quantum randomness has something to do with just maybe these pie slices get infinitely thin, basically. And so then any small perturbation around this angle will give you that uncertainty to give you a 50-50 chance of observing a plus h bar over 2 or minus h bar over 2 for the spin. But it's still, you could still say, well, you know, the spin still has some orientation to it. You just, you know, don't know what it is. And so then that's where the kind of randomness occurs. But quantum mechanics isn't like that. There's no local reality associated with the spin direction. And I'll give the example. Maybe it may make more sense when I do the
Okay.
actual problem. So here's the setup. You imagine sending these two spins off into two different people, and then they perform some measurements on them, right? And we imagine this red person measuring in some direction B1, and the blue person measuring in some direction B2. So this is person 2 over here, and this is person one in red. So we know that if we measure the following B1 or 2, this operator, the spin direction in direction B1 or 2, we know that the possible values there, right, are going to be plus or minus 1, just without the h bars over 2. This is just sigma. So the value of that measurement when you take it is going to be plus or minus 1. So let me call these things, the results of these measurements, epsilon 1, 2. It's what the person measures either up or down, along that direction. And so if we repeat the measurement over and over again, then what would we get? We could get, for instance, the expectation value of epsilon 1, epsilon 2. What would that be? Well, that would just be the sum over the possible values of epsilon, which again are plus or minus 1. And it'll be, epsilon 1, epsilon 2 times the joint probability of observing epsilon 1 and epsilon 2. So this would just be the probability you get up, up, plus the probability you get down, down, minus up, down, minus down, up. And so good, you have that. So how about now the people measure in 2 directions? So we keep sending them these spin singlets, and they'll measure them in direction B1 and B2. And suppose they also can measure in direction B1 prime and B2 prime, right? So then you can have B12 prime also. And that would have its own associated epsilon 1, 2 primes, okay? So then in principle, you can define the following quantity, right? This X. And the X would be the following. This is just an invented quantity, but we could measure it. It's a measurable thing. And it has the following form. Remember, these are all plus or minus 1s. And it's just a cleverly constructed quantity that's going to demonstrate something paradoxical about quantum mechanics. We'll see. So this thing, and we can factorize this to look like the following. So there's a kind of implicit assumption here, right? It's that these measurements all coexist in this, even if we don't make them, right? It's the idea here is that if we measure along 2 directions, then in principle, if we measured along some other direction, we would have gotten some other value. But this is, you can only construct this kind of X if in principle that other measurement, this prime, has a value that you could have calculated, could have measured. That's a meaningful thing to think about. And we know in quantum mechanics it's not going to be true, but we're going to try this anyway. So what's the idea here? Again, the measurements only give you plus or minus 1, right? So there's only really 2 cases to consider. In case 1, for instance, you would have epsilon 2 is equal to epsilon 2 prime. Then you would have, of course, epsilon2 plus epsilon2 prime would be plus or minus 2. That's one possibility, and this would be 0. So this quantity would be plus or minus 2. In case 2, epsilon 2 is equal to minus epsilon 2 prime, right? That's when they're opposite directions. Those are the only two possibilities if everything's just plus or minus 1. Either they're both 1, they're both negative 1, or one's plus 1, the other one's negative 1. Those are the only options. So in this, when they're both in the same direction, you get, they're both plus 1, you get plus or minus 2. Otherwise, you'll get epsilon 2 prime minus epsilon 2 is equal to plus or minus 2. So it's the opposite. Then, if this is true, then this guy vanishes and these guys are plus or minus 2. So no matter what you do, this x only takes on 2 values, which is plus or minus 2. If there's a sensible way in which we can think about, these measurements simultaneously, in the sense that even if we don't make those measurements, then this has to be a valid thing, right? That there's only 2 options here. Either, you get plus 1 for both of them or minus 1, and then you have this condition, or you get plus 1 and minus 1 different values, and then this is the only possibility. Either, this is 1 minus minus 1, so that's 2, or it's minus 1 minus plus 1, so that's minus 2. So those are the only possibilities. And so x is always plus or minus 2. So if you were to construct such a thing under this assumption of being able to think about the results of those measurements for those spins simultaneously, then the only possibility here is that x is plus or minus 2. And so in general, then, if you average over many experiments, right, and you measure this x, you take its absolute value, then we must have that it's less than or equal to 2, because if you keep averaging plus or minus 2, it's going to be either 2 all the time or negative 2 all the time, or it's some mixture of the two, and so it'll be smaller than 2. So this is a strict condition that you must have, and this is called a Bell's inequality. And we'll see that quantum mechanics violates this inequality. So that's really weird, because it means that you can't think about measurements in 2 directions simultaneously, even as just an aspect of reality, like a counterfactual, if you want. Could we have thought about the result of some measurement of the spin in some other direction? The answer is no, you can't. And it's not like that property of the spin and of the measurement of the spin in that direction is just not like part of reality. So that's the idea, and we'll see how it's violated. And the way, again, I can draw this little pie chart. The way you think about it is these 2 directions. So you have the red and the blue. So you have the red person measuring along 2 directions, B1 prime and B1. And you have the blue person measuring along some other 2 directions, B2 prime and B2. And the idea of, the assumption that's implicit in the construction of this Bell's inequality is that you can in principle know the value of every of these measurements, even if they're random, so, maybe there's just some kind of pie chart that tells you, even if it's random, of what result you'll get if you measure, along a particular direction. Maybe there's many, many different sectors in here that describe the randomness that you would find, but it's still knowable, right? You can still know in principle if you measure along that direction whether you'll get plus or minus 1. And same thing over here. Maybe there's lots of different sectors, right, of plus or minus 1, and that it's in principle knowable what you're going to get when you measure. right? This is like I can't draw the pie chart very well, but you can imagine some disk like this, right? That just, as a model of reality, right? So, there's this idea of, this is also related to local hidden variables. Maybe this pie chart that sort of tells you what the outcome is, even if it's random, it's just very finely spaced pluses or minuses here. Maybe that aspect of it is described by some hidden variable that, tells you about this pie chart. That's still an element of reality, but it's not. It doesn't work that way. So, and quantum mechanics shows you that it doesn't work that way. It's just that these are not properties of the spin that you can know simultaneously, even if they're random. So, just okay. So, quantum mechanics. What does that tell you? Any questions or before?
What is the name of this paradox?
Of what?
Of the paradox. What is
it's
there
the
a name?
Yeah, it's the EPR paradox, Einstein,
okay.
Podolsky-Rosen paradox. Okay. And again, yeah, the paradox is that the spins are anti-correlated for the singlet, no matter how you choose the measurement. So if this guy measures along X and this guy measures along X, then they're always anti-correlated. So as soon as this guy measures along X, the ones over here will be perfectly anti-correlated along X. And conversely, if he measures along Z, then they'll be perfectly anti-correlated along Z. But if he doesn't, then they won't be, right? And so that's the paradox. It's as if there's super luminous, it's as if there's faster than light communication between the two that tells you that this guy measured along some direction. So the spin has to be perfectly anti-correlated along that direction. It's like quick change so that to be anti-correlated along that direction. And that's the weird part of it. And
see that's why I thought, like, is if you have two boxes and you have a left shoe and a right shoe and you send the one box,
yes,
you open the other box, you have the left shoe in that box, you automatically know
yes
that the other person has the right shoe.
Yeah, that's right. But the weird thing about this is that depending on how you open the box, how you measure, the other person gets the correct right shoe for that particular way of opening the box.
Yeah.
Right.
Yeah, that's weird.
Imagine opening the box a certain way reveals like an orange, and depending on how you open that box, the other person, if they open the box in the same way, they get the opposite result, right? But if you open your box in some other way, and the other person opens the box in another way, then they're not necessarily opposite of each other. And that's the weird part, right? It's like as if the two shoes know about which way the person's opening the box.
Yeah, so in this way it's different than that because you have to correlate to like a position. That's what I wasn't thinking. I was thinking just opening a box, position didn't matter. But in this case, yeah. So like you said, if I opened it together the same, I get the opposite. You get the opposite one, which makes sense. But if he opens it up a different position, like the X, and I'm looking at the box in the Z,
yes,
it would be just random. He could get another left shoe possibly.
Exactly, and that's the paradox.
Yeah, that's weird.
It is. But the point is, and why do you pick two? If you think about what you're doing in your head when you're imagining the paradox, what you're doing is you're comparing two different possibilities, right? You're comparing the ability of the person to open it in one way and another way, right? You're imagining them measuring along Z and then along X, and they're like, whoa, that's a paradox. But what quantum mechanics tells you is you can't consider those two things simultaneously. They're not compatible measurements. So there is the spin just doesn't have that as an aspect of its reality, the value of the measurement in both, the Z direction and the X direction. They're just fundamentally incompatible. So that's but then we'll see. And that's what you're doing in this construction of this Bell's inequality, right? You're imagining two different measurements along like X and Z, and then comparing it, what would happen with the two different people opening the boxes in two different ways.
So that actually makes a lot of sense though, because he isn't really getting another left shoe of what I had. that person would have to do the same Z direction. And then
Yeah.
that's my right shoe that I sent out of 2 shoes. But if I were to do X, it would be the left, and the guy would do X, and he would get the other right shoe. But because they're not compatible, you can't just change it up. One can't do Z and one can't do X.
Well, they can do up, you just can't. So in the end, what happens? Some person measures along one direction, another person measures along another direction. That's it. The
right.
paradox only arises when you think about doing both things and having simultaneous values for
X and Z.
for one or the other. For, you know, but I'll show you exactly, you know, logically what we've done here is assume that, right? What we've done here in constructing this X is we're assuming that we could have measured, you know, left or right shoe or plus or minus 1 along 2 different directions for the same person, right? And for the other person. So that's why there's 4 total directions, and that's what we're thinking about. Saying, let's do an experiment where we measure, you know, B1 and B2 along some direction, and maybe B1 prime and B2 prime along some other directions, and we're comparing those 2 things. And if all those things have definite values, that even if they're random, then you can construct this X, and this X is always plus or minus 2. And so this is the inequality that must be satisfied. But you'll see that quantum mechanics violates it. So all right, so let's do the quantum mechanics. So in quantum mechanics, let's assume that B1 is along the Z direction. That's easy. And let B2 be some angle theta away from the Z-axis. Okay, so we know then that the spin up along the B2 direction, that's going to have the following form, right? It's cosine theta over 2 up arrow in the basis that, you know, we're familiar with. Like that. So there will be an associated probability amplitude, right, of measuring the spin in the up direction. What's that? That's going to be the up direction for B1, tensor product with well, with this state here. I don't know a good way to write it, maybe like up arrow B2. Right, so this is the first experiment. One guy is measuring along Z direction, the other guy is measuring B2, which is some angle theta away. So the probability that you measure plus plus, right, would be this probability amplitude. This, you know, dotted into the singlet state. And the singlet state, right, is up, down, minus, down, up. So the minus, down, up part, that dots to 0 because up dotted with down is 0, or orthogonal. So this whole thing just becomes 1 over square root of 2. It just picks up the up piece. You get up tensor up, you know, B2 dotted with up, down. It's the up, down part. And so you see that picks up the down component of this guy right here. So you get 1 over square root of 2 sine theta. All right, so what does it mean? It means that the probability of measuring up is sine squared theta over 2. Oh, sorry, this is theta over 2. Sine squared theta over 2 divided by 2. So that's that. Down, down is quite similar, right? You'll get the same thing actually if you do down, down. And so I won't go through the answer, but it's the same procedure, you know, you do down, down or up, down, or, you know, all the combinations, you dot it into this thing, you do the dot product of the tensor product states, and you get these values. So I showed you sine, but, you know, the other ones are pretty easy too. Yeah, and you get this guy, which is 1/2 cosine squared of theta over 2. So what do we get? We get that if you want the expectation value of, say, epsilon1, epsilon2, then that just gives you, right? It's back what I said before, this guy. Up, up, plus down, down, minus down, down, this guy. In quantum mechanics, that quantity is just going to be sine squared theta over 2 minus cosine squared theta over 2, which is, using a trig identity, it's minus cosine theta, which is minus b1 dot b2. Right, so that's what quantum mechanics tells us about the average of this quantity, epsilon1, epsilon2, it's minus b1 dot b2. Again, this is, right, measuring along direction b1 and direction b2. And we just, without loss of generality, chosen b1 to be the z-axis and b2 to be some arbitrary angle theta away. Okay, so that's one part of the calculation. So what are some good, now we want to compute this x, right? We want to know what happens to x with quantum mechanics. And so it's good to choose a particular, choice of directions to measure to sort of maximize the violation of this Bell's inequality. So we're going to choose B1 to be along the z-axis again, it's B1. Then B1 prime, we're going to choose along x. So incompatible measurements, as we know, right? And then we're going to choose B2 to be at 45 degrees away from these guys. So I should have, yeah, maybe I should make these blue, I guess, for the second person. And these guys, I guess, can stay red. But you get the idea, right? It's these two directions and then these two for the other guy. This is B2 prime and this is B2. Okay. So let's compute the expectation value of x. What would we get? We get, you know, expectation value of these two guys plus these two guys plus these two guys. Right? And we know what each one of these is going to be minus the cosine of the angle between those corresponding directions. So this, the direction between 1 and 2, let's see, 1 is over here and 2 is over here. So that's 45-degree angle. So that's minus cosine pi over 4. Here, epsilon 1 and epsilon 2 prime, that's the angle between 1 and 2 prime, that's also 45 degrees. What about 1 and 2 prime? That's the, those are the two primes. So that's this guy and this guy. That's again 45 degrees. That's minus cosine pi over 4. And then the other one is epsilon 1 prime, which is this guy, this direction, the 1 prime, and 2, and that's this guy over here. So that's 1, 2, 3 times 45 degrees. So that's plus cosine, and you know there's a minus sign here, so it gets a plus cosine of 3 pi over 4. And what's that? That's minus 3 over square root of 2 from these guys. And this one gives you a minus 1 over square root of 2, which is minus 2 square root of 2, which is bigger than 2. Well, it's the magnitude is 2. So the magnitude of x is 2 square root of 2 is bigger than 2. So it violates this argument that we had before, where if you're able to think about the values of these measurements simultaneously, even if they're random, then you should always get plus or minus 2. But you see in quantum, you should always get, you know, that x is less than or equal to 2, right? If you just think about these as random numbers, right? But they're not. They're they're correlated, and you can't think about them simultaneously. So there's no sense in which you can think about values of the spins in terms of, you know, some local hidden variables, as they're called, that will determine the value that you get plus or minus 1, even if it's random. Because quantum mechanics violates Bell's inequalities. If you actually compute the average of this x absolute value, you get something that's bigger than 2.
So that's just proving that they're not, you can't think of them both ways, because if you do that, if you try to, you know, it like you said, it's got to be greater than 2. If it wasn't for that, if you're in taking the magnitude, then there could be a possibility if it came out the same, you know, but because of it, it's greater than 2 in this case. That's why you can't compute that magnitude, right?
Well, it means that that x is not a property of the system. There's no sense in which x, which is the results of these measurements, is like a physical property of the system. It's not measurable. It's not an element of their reality. You can't think about measuring a spin along z and x, the values of those measurements simultaneously, even if, you know, you allow them to be random. So what I did here, right, I constructed this x and I said, just suppose these are all random. They're just plus or minus 1, and who knows what their distribution is. I argued just very, you know, generally that no matter what, if these are just some random numbers, then you should always get this Bell's inequality. But quantum mechanics violates this inequality, so it means I can't think about these guys as having some random values. It's just not an element of reality. So it's, you know, it tells you that a theory with so-called local realism, which would correspond to maybe having some local hidden variables that would tell you the results of the measurements, even if they're random, you know, along 2 different directions, like a little pie wheel with lots of little random segments in it, that kind of capture the quantum randomness. That's literally not how reality is. It just doesn't work that way, because quantum mechanics violates this inequality. So,
right. So there's no like predetermined or destiny basically for that, because if you had a wheel like that, it would be almost predetermined, because you could say, oh, I know it's going to be.
Well, yeah, it means that you can't work harder and develop like a more precise measurement and work even harder to try to get rid of the quantum uncertainty, right? It's like you'll never be able to do that. You'll never be able to construct this wheel.
Right.
So it tells you that, you know, quantum mechanics is here to stay. It's not going to go away. You're not going to be able to construct a better theory that, you know, looks like a classical theory that maybe tells you how the randomness comes about, for instance, right? It's just not going to happen.
So can you conclude that quantum mechanics is not complete and there are hidden variables out there, and then quantum mechanics cannot capture those?
I suppose that's what the original conclusion of the EPR paradox was, but I don't like to view it that way at all. I think it actually is the opposite of that. It tells you that quantum mechanics is never going to be described by a theory with local hidden variables. That is what this says, because a local hidden variable would tell you about locally the measurement of the spin. So whatever that extra theory is, it would certainly have to have non-local hidden variables, which would mean that the spins are somehow non-locally connected to each other through some hidden variable that you can't measure. I find that as an unsatisfying resolution of the paradox. I prefer to think that it's just not an element of reality that you can have these simultaneous measurements. There are certain there are certain statements that just don't have truth values. We just can't make them. So I prefer to think of it that way. I'm sure there are, lots of opinions about it, but hopefully at least this example makes sense. The first step is getting this example, and I think then all the philosophical stuff even I'm kind of hazy about.
Yeah, but that's a good example. Thanks. I'm gonna probably use that to show.
Okay, any more questions about that? EPR. Yeah, it's tough conceptually to grasp, but
Isn't that quantum mechanics in general, though? I mean, we don't have.
well, that's why we've been doing the Hilbert space math and not dealing too much with this, but this is our first, and I think the only way to make sense of it really is to do the calculation to see what happens. Because just thinking about, so what do we do here, right? It's really funny. We constructed, yeah, I just maybe emphasize this again. This X is like a conjectured, conjectured measurement that we're gonna make, right? Where all of these in principle have some values simultaneously, and they could be random, right? And we repeat this experiment over and over again, and we get random numbers for these, and no matter what happens, we always get plus or minus 2, right? Because if they had definite values, then that's what we would find. That's how we would do it, right? And so logically, the logic says that if these all have definite values, even if they're random, we average over and over again, we always get this Bell's inequality. But that's not what quantum mechanics tells us to do, right? Quantum mechanics tells us to take an expectation value of an operator. And so we can consider this as an operator where these are, the associated spin measurements along those directions. And we compute the expectation value with respect to the spin singlet, which is the state that we're using. And that's what we're doing here. We're actually calculating those probabilities from the expectation value here. And that's what we did using the Bras and Ketz. And now we're doing everything properly within quantum mechanics. And so we're actually calculating this expectation value of this X using, the actual states, which is assuming that, we're in a singlet state and then we're measuring along these particular directions, just as an example. And after you do that, you see you get something really weird that is not compatible with our logic about the values of epsilon 1 and 2, these guys simultaneously. What we get is that you get something that's actually violates that Bell's inequality. So you can't think about them as just having some joint distribution where you just get some random values. Doesn't work that way. So there's some aspect of this that we're not getting right, and we're not getting right is this idea that you can, in principle, know simultaneously the results of those measurements.
Right. And so we'd have to add some non-local thing, like you were saying.
Yeah, in principle, you could get this to work out if somehow the random numbers here and here, they kind of knew about each other. So there'd be some other like bigger pie chart that kind of connects the two.
Yeah.
Yeah, that would be the idea of a non-local hidden variable.
Yeah, which is more likely than a local hidden variable because of this. And that's what
because of this, there are no local hidden variables.
Yeah, that's right. Well, I mean, like you said, people might argue and say, "Oh, there might be," but I'm saying that I agree with you.
Logically, it doesn't. You can't, right?
I know, right? It does. Yeah. If you showed me this, I wouldn't think that. I'd say it has to be like a bigger system outside in order to describe it.
Yeah. But I think
even then,
I think quantum mechanics is perfectly complete, and it's just that's the way nature is. There's just some things don't have truth values. Not everything has to be certain. So it's a nice quote by Max Born you could read on his wiki page. Maybe I'll read. It's his Nobel Prize lecture. Maybe I'll read it. I'll just actually I agree with Max Born's philosophy about these things. Let's see what he said. So he got the he got the Nobel Prize for you know, basically the foundations of quantum mechanics. He was the one who worked on the canonical commutation relation, and he also first introduced psi star psi as the probability density. So what do you say? He got his a good quote. Let's see. What is that? Yeah, I believe that ideas such as absolute certitude, absolute exactness, final truth, etc., are figments of the imagination which should not be admissible in any field of science. On the other hand, any assertion of probability is either right or wrong from the standpoint of the theory on which it is based. This loosening of thinking seems to me to be the greatest blessing which modern science has given to us. For the belief in a single truth and in being the possessor thereof is the root cause of all evil in the world.
That's actually pretty true.
Funny quote.
That's awesome.
Yeah.
But yeah, so, you know, but there is other ways to think about, you know, resolving this violation of Bell's inequality. There are non-local hidden variable theories and things like that. And, you know, the original conclusion of Einstein, Podolsky, and Rosen, as I understand it, is that quantum mechanics is an incomplete theory. But I take the opposite view, I suppose.
Yeah.
I think it tells you that uncertainty and having certain statements not have truth values, like is just a feature of reality. But, you know, there's definitely different interpretations and things like that. So I don't want to harp too much about it. So.
All right.
All right. Any more questions about that?
The computing side of things, right?
Yeah, we're going to talk about computing. Computing is cool. But yeah, hopefully that last year, I think it gets better every time, this explanation, but it's still hard for me to explain it correctly, this Bell's inequality thing. But,
I think that was a pretty good one. I mean, it helped understand that how it doesn't work out for that, you know. I think you showed it.
all right, well, that's good.
You convinced me. You convinced me, at least.
All right, so let's talk about quantum computing a bit. Well, quantum computing is basically just manipulating tensor products of qubits. So it's just like what we had before. If you know, you have a qubit Hilbert space and you tensor product it with a whole bunch of other qubit systems. And much like classical computing, you have a register of bits. And a register is just a set of qubits and a tensor product of them. And instead of up and down, it's easier to think about zeros and ones because those are like the classical bits. So, you know, it's still a Hilbert space, two basis vectors, and we're just gonna call them 0 or 1. And a register you can think about as a set of some number of qubits. And you know that if you have something like this, we can interpret this, right, as like a number, right, in binary. So you would have, this would be 1, you know, this is the 0th place, this is a 2, this is the 2 to 2, the 4th place, so this would be 2. Here is 4, right? If you wanted 3, you would have 1, 1, 0. That would be the qubit. That would be the qubit. I mean, that would be the bit register corresponding to, you know, a 3. So you can, so that's what you have. You have the tensor product states, and you know that you can have linear combinations of them as you would in a Hilbert space, and some linear combinations are entangled and some are not. And it turns out quantum computing, you can prove pretty rigorously that there's only two things you can do. It's amazing, but true. One thing you can do is just a unitary evolution of a single qubit. So you would take some unitary, and everything else could be the identity for the rest of the register. So you just apply some unitary operation to one of these bits, or qubits. That's one thing you can do. And the other operation is a CNOT gate. And it just exchanges the states of two qubits. And literally any quantum computing algorithm, you can break it down to just these steps. Now, there may be very many of them, but this is all you ever need. So that's all you ever need to understand. This is a unitary evolution of one of these guys, and then the exchange thing. And so what? So what is a good, so yeah, and I'll talk about the CNOT gate in a moment, but one of the most important unitary evolutions is called the Hadamard gate. So it's a unitary, but it looks like the following. Remember, it's an operator unitary, it's a 2x2 matrix. It looks like that. And what this does is it takes any state and it gives you a superposition of the constituent of 0 and 1. You just work out what it is, right? It's just matrix multiplication. And there's also, you can see what it does on 1. That's just why is this cool is because you see it takes a 0 and gives you a superposition of 0 and 1. So if you take this unitary evolution and you apply it to every single qubit in like a register full of zeros, then you would get a linear combination of all the numbers, right? You get all the possibilities of the numbers, right? You get all the possibilities for 0 and 1, because each 0 converts to both a 0 and a 1. Then you multiply them all together in the tensor product, and you get the whole thing. You get you can construct a superposition of all the possibilities of the bits. So this is tensor product n times. So you apply this on each of the qubits on like the 0 register, right? And that should give you all the numbers from 0 to 2n minus 1. The 2n minus 1 would be all ones in your register. And I'll just denote this x. These are the number states, right? Here, I'll put these in caps. Just a shorthand. Okay, so that's pretty useful. And this is the sense in which, people say weird things like quantum mechanics, quantum computing lets you do like parallel processing or whatever, because it's as if, if you do something with the superposition, it's as if you're doing something to all the numbers, to all the possibilities for the bit register. But that's not how it works at all, because in the end, you still measure something. You still you have an input and you read out an output, and the output's always classical. So that's not really, and remember I showed you that the information content, even in a single, in a quantum bit, is the same as in a classical one, so that you're not actually gaining anything. It's not as if you're doing some crazy parallel processing or anything like that. It's different. So I'll show you how in a moment. Oh, well, I'm out of time, but I'll show you how next time. But at least you got the idea of how you would set up the unitaries. Next, I'll show you a CNOT gate, and I'll do a little computation. I'll show you how the Deutsch algorithm works. And then that'll be
Great.
quantum computing. Yeah, hopefully you'll see that it's not anything. It's cool. It will definitely make for very fast computers, but I'm not sure what is new about them, like in a very deep computing sense, other than, you get some really much faster increases in the number of steps it takes to compute something. But the kinds of things you're computing, I don't know. You're still reading out zeros and ones. You're still putting in zeros in ones. So in the end, since our brains are kind of classical, I'm not sure. I'm sort of meh on quantum computing, but I'll show you how this computing algorithm works. To show you how it can get you speed up for certain things. But yeah.
Cool. Thank you.
For certain things, it provides some approximation, just an approximation to the solution.
What's an approximation?
Like when you measure the quantum algorithm, it's just the expectation value gives you some approximation.
Yeah.
Oh, that's a very interesting point. It's true quantum computing is not like that. The way you set up the measurement is such that it's a measurement that gives you something with 100% probability. And I'll talk about that next time. So yeah, you're right. In principle, if it's arbitrary kind of measuring, then you would get some expectation. You'd get the quantum randomness would come in and give you some probability distribution over possible measurement outcomes. But the way you design these quantum computing algorithms is always such that after you do everything and you take your measurement and you read out your register, that you always get a well-defined you get a concrete answer, because you need an answer. I mean, it's a computer. It has to give you the same answer every time you run the program. Otherwise,
so even IBM's, that's the computer that they've been using, and I've since I started here at UT, they were, like touting it stuff. It's the same principle though, right? So that was that's not like a D-Wave machine. It's IBM Q experience, which every one of us can get into for free and use. And when I run it, it usually gives me a probability of something, like it was 1 probably, it gives you like a curve.
Yes. So there's lots of subtleties to this. One is that a lot of these quantum computers that are being developed now, they're more like quantum system simulators. So they're in a sense, they act like a quantum system, and then you could get probabilistic information out of that. But to me, quantum computing, what that would mean is you use quantum operations to get some result, to calculate something, to factorize a prime number, and factorizing a composite number into large primes, right? Sort of like hacking an RSA a type encryption, where you have a large composite number as a product of 2 very large primes, and you have to factorize this number. So those are concrete operations, and I'll show you next time the Deutsch algorithm, which gives you a property of a function. But those are calculations. They're not probabilistic. They give you an answer. They give you the 2 prime numbers.